Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Bismillahirrahmanirrahim. Welcome back. Chapter number 9, that is about deflection of beams. So in this chapter we are going to cover the deformation of beam under transverse loading, equation of elastic curve, then we will have a certain sample problems, method of superposition and many more topics. So we will cover this chapter in different parts. So let's start this chapter. So from our previous knowledge of chapter number 5, that is about beams, shear force and bending moment of beam under given loading. So let we have a simply supported beam. Let this is a simply supported beam and that is loaded with a concentrated load P. So from this we have already studied so that we can get shear force and bending moment. Clear? Once you get this shear force and bending moment, you can calculate the shear stress, that is represented as VQ over I into thickness T. Clear? Where V is shear force, Q is the first moment of inertia about neutral axis, I is the second moment of inertia and T is the thickness. Similarly, from bending moment we can calculate the bending stress, that is represented as MC over I. Now if you look at this beam that is under the concentrated load P, so definitely if we take the section of this beam at this point, so at this support there will be a reaction force and there will be a reaction force. Let this is RA reaction at A and at this B. This is point B and this is point A. So our beam will, after sectioning the beam at this, so our load will be like this. There will be a reaction force RA and there will be a shear force with a movement at this point, and let this distance is x. Clear? Similarly, if you look at this from our previous knowledge, we can calculate the shear force and bending moment, and we can use this shear force and bending moment to find the shearing stress and the bending stress. Now in this lecture we are going to calculate the deflection of beam under the loading condition. So if this is the beam and that is loaded, so definitely there will be a deflection of the beam. The beam will deflect like this under this loading. So let this is the initial x-axis, so there this will be the deflection, that is known as y. Clear? So in this chapter we are going to cover how to find this deflection as well as slope. We can also describe them by using another problem. Let we have a cantilever beam that is acted upon by a concentrated load at the end, that is P, and total length of the beam is L. Clear? So if you section it at this point, so I will represent it over here. So this is the P load. Clear? There will be a shear force and there will be a bending moment M as well. Clear? And let this is the distance x. Now in this beam, if I draw it by using a line, this is a cantilever beam and acted upon by load P, so there will be a deflection in this beam due to this load P, and this deflection will be in the direction of load P, and this is the original x length of the beam in x direction. There. Now this deflection is y. From this point to this point, this deflection is y, and we are interested to find out this deflection y. Also with this deflection you can see the slope of this line will be theta. Clear? with respect to this x and this theta. So this theta is known as slope, and we can find out this slope at any point with respect to x. So in short, in this lecture we are going to find out this deflection as well as slope. How we will calculate them, or how we will find them, so let's move further. So you can see this is a cantilever beam that is fixed at point B, and at point A there is a concentrated load P that is acting at point A. Clear? So from our previous knowledge, that is relationship between the bending moment and curvature for pure bending valid for general transverse loading. So this is transverse loading because it is perpendicular to the axis of the beam. So from our that knowledge we have 1 over rho is equal to moment divided by E into I, where 1 over rho is the curvature and m is the bending moment, E is modulus of elasticity, and I is the second moment of inertia. Clear? So this 1 over rho is curvature and rho is radius of curvature. Again, we will use this equation that will help us in finding out the deflection. So you can see that this cantilever beam is acted upon by concentrated load at point A. So the length of this beam, total length of this beam is L, and this X varies from left side to right side. At left side we have at x is equal to 0, and at right side x is equal to L. So x is greater than or equal to 0 and less or equal to L. So if we use this variation of x and put the value in this moment equation, because moment is a function of x. So if you use this x value, the x value changes, varies, so bending moment also varies. So if you use this x in this equation of bending moment, so in this case it will be this moment mx will be equal to minus p into x. So for any x value, the bending moment will change. So if you use the variation of x, the bending moment will change, so radius of the curvature will also change. So you can see cantilever beam subjected to concentrated load at the free end. So 1 over rho is equal to, if you put the value of mx, that will be equal to minus px over ei. So curvature varies linearly with x, because at free end at x is equal to 0, when you put x is equal to 0, so movement will be 0. So 1 over rho will be equal to, this value will be 0, so 1 over rho will be equal to 0. It means the radius of curvature at point A is infinity. Similarly at point B, where x is equal to L, so if you put x is equal to L, so moment m at x is equal to L will be equal to minus p into L, and that will be not equal to 0, because that will be 1 over rho is equal to minus pl over ei, and that will be not equal to 0. It means so radius of curvature will be ei over pl, because it will be the inverse. I will write it over here. 1 over rho b will be equal to minus pl over ei. Clear? So if you want to have radius of curvature, so it will be equal to ei over pl, which is same that is mentioned over here. Okay, now you can see this is an overhanging beam that is subjected with this load 4 kilonewton and 2 kilonewton at point B and D. So there are two support. One is pin support at point A, and at point C there is a rolling support. So for solving this beam, we must need the reaction forces at point A and B that can be calculated by the knowledge of statics that you have studied earlier. So you can find RA and RC at this point. Okay, so reaction at A and C is calculated over here. That is reaction at point A 1 kilonewton and reaction at point C is 5 kilonewton. So you can also solve them, solve it to find out these reactions. Clear? Now, as we know that 1 over rho is equal to m into x divided by EI. So for that beam, we need the equation of movement. Clear? So we will find the equation of movement, our bending moment diagram. We can also find out the this bending moment from this bending moment diagram. So you can see, if you solve it, so you will get the bending moment diagram over this. So you can see that bending moment is maximum at this point B, and bending moment is also maximum at point C, because here the load, due to loading, there will be a curvature effect. So you can see the one curvature is this one and other one is this one. Clear? So at the point of maximum bending moment, there will be a maximum curvature, which is shown over here. Okay, so curvature is 0 at point where the bending moment is 0, i.e. at each end and at E. So at point E, because there is a at point E there is a 0 bending moment, so curvature will be 0 as well. And at maximum bending moment, the curvature will be maximum. So beam is concave upward where the bending moment is positive, and concave downward where it is negative. So you can see this is concave upward where the bending moment is positive. So it is bending moment is positive at this point, so beam is concave upward. In upward portion it is concave, while at point C the bending moment is negative, so beam is so the concave will be in the downward portion where the bending moment is negative. Maximum curvature occurs where the bending magnitude of bending moment is maximum. So an equation for the beam shape or elastic curve is required to determine the deflection and slope. And this deflection and slope can be found by using by deriving elastic curve, which will determine the deflection and the slope of the beam under the loading condition. So we will now discuss that how to derive the elastic curve equation in order to determine the maximum deflection and slope. Okay, so equation of elastic curve from our elementary calculus that is used for simplified for beam parameters. So let this is the beam that is fixed at both and are simply supported beam. So due to loading there will be a deflection y at a distance of x from this point O, and there the slope of this line will be theta x, or with respect to x it is theta x. So y is known as deflection and theta x is known as slope. So from our elementary calculus we have that 1 over rho, that is curvature, is equal to d square y over dx square divided by 1 plus dy by dx whole square की power 3 over 2. Now if you see that this is the deflection, so this yx is deflection, and this is very small deflection. So if you take derivative of this y with respect to x, again this will be a very small number, and this very small number means this is equal to 0. So this equation, that is 1 over rho or curvature, is approximately equal to d square y over dx square. I will write over here this curvature is equal to d square y over dx square. Also we know that 1 over rho is equal to mx over ei. Clear? So let this is equation number 1 and this is equation number 2. 2. So if you this curvature is equal to this term and this curvature is equal to this term. So if we equate equation 1 and 2, we will get d square y, sorry, I will correct it. Okay, we can write it d square y over dx square is equal to mx over ei. Also you can write it as ei into d square y over dx square is equal to m of x. Now you can see that this is the equation and we will use it further to find out the deflection and slope. This is the second degree equation. So if you integrate this equation once, so you will get ei into dy by dx is equal to integral of mx into dx plus c1, where dy by dx is again equal to slope. So you can also write e into I to theta is equal to integral of mx into dx plus c1. Now this is the equation of slope. So if you integrate it again, so you will get ei y is equal to integral of dx into integral of mx into dx plus c1x plus c2. Clear? Now you can see this is the slope. This is deflection and this is equation for slope. So we will use this equation in order to find the deflection and slope. But again you can see that this equation contains C1 and C2 which is unknown, and for finding these unknowns we will use the boundary condition in order to find C1 and C2. We have different boundary condition for different type of beams under the loading condition. So we will analyze the beam and from that we will find the boundary condition in order to get these unknown C1 and C2. After finding C1 and C2, we will put them in this equation of slope and deflection in order to get a general equation for finding the slope and deflection. So these are the same thing you can use to find the beam slope and deflection. Now from our previous slide we get ei into y is equal to integral of dx into integral of mx into dx plus c1x plus c2, and this is equation for finding the deflection. Now you can see that we have different statically determinant beams, that is simply supported beam, this is overhanging beam, and this is cantilever beam. So we will look at these beams in order to find the in order to explain the boundary condition. Now for this simply supported beam, you can see this is supported at point A and this support is pin support, and at point B there is a rolling support, and there is a uniformly distributed load that is acting on this beam. Now if you look at this beam at this point A, x is equal to 0 and x is the length, x will be in this direction, in direction of length. Let the total length of beam is L, so x is greater than or equal to 0 and less or equal to L. Clear? So you can see that this simply supported beam at x is equal to 0, so you can see the deflection at point A is equal to 0, because you can see at point A there is no deflection. Similarly, at x is equal to L, the deflection at this support point is equal to YB, which is again equal to 0. So for simply supported beam at x is equal to 0, deflection at point A is equal to 0. Similarly, at x is equal to L, deflection at point B is equal to 0. For overhanging beam, again you can see that at x is equal to 0, YA is equal to 0. Similarly, at this point B at x is equal to, let the total length is L, and from this distance to point B, this is total distance A. So at x is equal to A, YB is equal to 0. Clear? Now, you from these two figures of beams, that is simply supported beam and overhanging beam, you can see that at support deflection is equal to 0. Now we will move toward the cantilever beam. You can see the cantilever beam is acted upon by a concentrated load at point B. So at fixed support, you can see the at x is equal to 0 at fixed end. This deflection at point A is equal to 0, and similarly the slope will also 0, because you can see if this is the horizontal line, so at this point A there the slope will be also 0. So at x is equal to 0, YA means deflection at point A is equal to 0, and x is equal to 0, slope at point A is equal to 0. So these are some boundary condition that has been used, that will be used in solving such type of problems in order to find out C1 and C2. Now we will move toward a sample problem in order to have a clear understanding about finding the deflection and slope. So the cantilever beam AB is of uniform cross section and carries a load P at free end. So this is free end. A. Determine the equation of elastic curve and deflection and slope at point A. So basically this is a cantilever beam acted upon by concentrated load. So you have been asked to find the equation of elastic curve, which is y is equal to function of x. So basically you have to find the equation of deflection in term of x, and then you will also have to find the deflection and slope at point A. So you have to find y at point A and slope at point A as well. So let's start with the solution of this problem. So if you take a section at this point, so your beam will be like that. So this is a point P, clear, and this is at point A. Now the length of this beam is L, and if you cut it at this section, so there will be a shear force V and there will be a bending moment M. Clear? So this bending moment is in counterclockwise direction, and this P into X is also in counterclockwise direction. So P into X plus M will be equal to 0. It means that M is equal to minus P into X. Clear? Now we know from our previous knowledge that is explained a little bit earlier, that EI into d square y over dx is equal, dx square is equal to m into x. We have done this over here. I will show you. Okay. So here you can see EI into d square y over dx is equal to mx. So we will put the value of this mx, which is equal to minus p into x. Clear? So we will get EI into d square y over dx square is equal to minus p into x. Clear? Now this x is basically x, I will write over here, x will start x will be start from 0 and it will be less than L. So from x is equal to 0 till x is equal to L. So if you integrate this equation once, so you will get EI into dy by dx square is equal to minus px square over 2 plus c1. So this is dy by dx, not dx square. Clear? So this is dy by dx is slope. Again, if you integrate it, so you will get ei into y is equal to minus px cube over 6 minus plus c1x plus c2. Now this is, let's say this is equation 1 and this is equation 2. This equation is used to find the slope and this equation is used to find the deflection. Now from our boundary condition for cantilever beam, as we discussed, that at x is equal to L, because this is the fixed end. So at x is equal to L, y is equal to 0, and at x is equal to L, theta will be 0. So we will use we will put x is equal to L, theta is equal to 0 in equation 1. Why? Because at x is equal to L, theta will be equal to 0, so this term will be 0. So we will have C1 will be equal to PL square over 2. Why? Because this term will be equal to 0 and this will be L, so PL square over 2 minus C plus C1 is equal to 0, so C1 will be equal to PL square over 2. Now we will put at x is equal to L, y is equal to 0 in equation 2. So we will get when we put y is equal to 0 in this equation and x is equal to L, so this you have to solve it by yourself. This C2 comes out to be minus 1 over 3 PL cube. Now you have both C1 and C2, so you can put them in equation 1 and equation 2. So you will have equation 1 will be like this, EI into theta, because dy by dx is equal to theta is equal to minus px square over 2, and C1 is plus PL square over 2. Similarly, the equation EI into y is equal to minus px cube over 6 plus this equation C1 is equal to PL square over 2 and XL, so it will be 1 over 2 PL square into x minus C2 is 1 over 3 PL cube. Now we have this equation that can be used to find out the slope, and we have this equation that can be used to find out the deflection. So if you divide this equation, let this is equation number 3 and this is equation number 4. So if you divide this equation number 4 by EI, so we will get here y is equal to P over 6 EI and take P over 6 common, so we will have minus x cube plus 3l square into x minus 2l cube, and this equation y is equal to P over 6 EI into minus x cube plus 3l square into x minus 2l cube is equation of elastic curve. Equation of elastic curve, because you have represented y as a function of x. So from our this problem we have determined the equation of elastic curve. Now you can also find the deflection and slope at point A. How? So I will solve it over here. Now you have this deflection equation and slope. So at point A you want to find the slope theta A. So at x is equal to 0, theta A will be equal to, at x is equal to 0, so this will be 0. Clear? So theta A will be equal to x will be 0, PL square over 2 EI. So theta A will be equal to PL square over 2 EI. So this is the second part. Now at x is equal to 0 we have to find deflection. Clear? And this deflection, if you put x is equal to 0, so it will be equal to minus 2pl cube over 6 EI, which will be equal to minus pl cube over 3 EI, because we have minus 2 which will cut with this 6, and this we have minus PL cube over 3EI. I hope this, by solving this problem, it is clear to you now how to find the slope and deflection and how to find the equation of elastic curve. Now let's move further. We will solve sample problem 9.1. So you can see there, this is overhanging beam that is supported. There is a pin support at point A, and at point B there is a roller support. At point C there is a concentrated load. So for portion AB of overhanging beam, it is given that for portion AB, only for portion AB, derive the equation of elastic curve, that is y is equal to f of x. You have to find the deflection equation in term of x, that is a function of x, and determine the maximum deflection, y maximum. Clear? And evaluate y maximum as well. Now the difference between part B and part C, both are to find the y maximum. So the second part is to find the general equation for maximum deflection, and the part C is to find the value of maximum deflection. So before solving this problem, as you know that first of all you have to find the reaction forces at point A and B, and this reaction forces can be found out by using the equilibrium method or by using your knowledge of statics. So you can find out the reaction forces at point A and B. Clear? So then after finding this point reaction forces at point A and B, so you have to find the expression for moment and derive differential equation for elastic curve. But remember that in question it is given that this is for portion AB of overhanging beam. So you have to find the moment equation for AB. Clear? And then you will use the integration method, double integration method, in order to find the elastic curve. Clear? and then applying the boundary conditions, so you will get the C1 and C2. After that C1 and C2, you will put them again back in that equation, so you will have the slope equation and elastic curve equation. Okay, so you can see here the reaction force have been determined, that is given as this is the okay, so you can see this is the reaction forces at point A and B, which is given as RA is equal to PA over L and RB is equal to P into 1 plus A over L. You can also find them by using knowledge of statics. Okay, no, so from free body diagram for section AD, clear? So if you cut this beam at this section or at section D, so you will get this beam like this. So there will be a reaction force at point A, and this reaction force is equal to PA over L. Now this is the length of beam, which is represented as X. So for movement equation will be this movement is counterclockwise, so M will be plus and this will be also positive, so that will be equal to RA into X is equal to 0. So movement plus RA is equal to PA over L into X is equal to 0. It means that movement is equal to minus PA over L into X, where X is greater than 0, greater or equal to 0 and less or equal to this length L, which is portion AB. Clear? So now we have this moment equation for portion AB. So we will use this equation in equation that we have discussed earlier, that EI into d square y over dx square is equal to m into x. So you will put the value of m over here, so this equation will be like this. This differential equation for elastic curve will be EI into d square y over dx square is equal to minus PAL over x. Now you will integrate it once, so you will get EI dy by dx is equal to minus 1 over 2 PAL over x square A over L into x square plus C1. Now this is the slope equation. Let this is equation 1. Now if you integrate it again, so you will get EIY is equal to minus 1 over 6 PAL x cube plus C1 x plus C2. I hope these things are easy for you, how to integrate and how you will get this. Clear? Now you have this equation 1 and equation 2. You will apply the boundary condition in order to find this C1 and C2. So you can see this is a overhanging beam. So at support point, we have already discussed that at support we have 0 deflection. So at x is equal to 0, we have y is equal to 0, and at x is equal to L, y is also 0, because these are the support and deflection at the support will be 0. Clear? Okay, so at x is equal to 0, y is equal to 0, and x is equal to 0, x is equal to L, y is equal to 0 as well. Okay, so when you put at x is equal to 0, y is equal to 0 in equation 2, at x is equal to 0, y is equal to 0, so we will have C2 is equal to 0. I will write it put in equation 2, because this equation is about deflection. So deflection is 0 at x is equal to 0, and deflection is equal to 0 at x is equal to L. So C1 will be, C2 will be equal to 0. Now if when you put at x is equal to L, y is equal to 0. So if you put x is equal to L and y is equal to 0, so you will have C1 will be equal to 1 over 6 PA into L. You can also solve them. Now you have the value of C2 and C1. You can put it. I have, again I will let me clear it. Okay, so erase option. Okay, so I will erase them because I have already told you about these things. Okay, so you can see that at x is equal to 0, y is equal to 0, so C2 will be equal to 0, and at x is equal to L, y is equal to 0, so when you put y is equal to 0 and x is equal to L, so C1 will be equal to 1 over 6 PA into L. Now put the value of C2 and C1 in both equation 1 and equation 2, so you will have this equation 1 will become equal to EI dy over dx is equal to minus 1 over 2 PAL into x square plus 1 over 6 PAL. Again, so if you want to have this slope which is equal to dy by dx, so you have to divide the equation, both side of the equation by EI, so you will have dy by dx is equal to PAL over 6 EI into 1 minus 3 into x by L square. Now if you put the value of C1 and C2 in equation 2, so you will have the equation will become like this. And for finding the equation of elastic curve, so you have to divide both side by EI. So y will become equal to PAL square over 6EI into x over L minus x by L whole cube. And this equation is known as equation of elastic curve, because this y is the function of x. Clear? So we have find out the equation of elastic curve for portion A and B. Now for part B we have been asked to find the y maximum deflection equation, and in part C the value of maximum deflection. Now you can see that the equation of maximum deflection or the value of x, or at for the value of x, this was the beam, so for the value of x where the deflection will be maximum can be find out by taking the first derivative of this deflection is equal to 0. dy by dx is equal to 0. So if you take the first derivative of deflection with respect to x is equal to 0, so you will get the value of x at which this deflection will be maximum. So we have already this dy by dx, so if you put this dy by dx is equal to 0, so you will get the value of x for which deflection will be maximum. So you can see over here, so dy by dx is equal to 0, and the value of x for which the deflection at which the deflection is maximum is equal to 0.57 L. It means you have L, so when you multiply it with this value, so add the value of this x, the deflection will be maximum. So this is the general equation for finding the deflection. Okay, so now we will also evaluate the corresponding maximum deflection. Okay, so we have the deflection equation like this. This is the deflection equation. Clear? Now here you will put the value of x that has been calculated here. Clear? So when you put the value of x in the equation, you have P you have A L square 6 E I, all the values are available, so you can calculate Y max, and this Y max is equal to this value. Clear? So this is the equation, this is the equation, and when you put the value of P A L square 6 E I, again this is given in the question. Let me show you. At the start of question, this was given I, E, A, L, P, all the value were given, so you have to put them. Clear? So you will get the deflection, maximum deflection is 0.238 inch.